Alrighty, howdy folks. Our focus is going to be on 3.3 today, and this is about derivatives of trigonometric functions. Okay, one of the first things we'll do is we'll prove that limit of sine theta over theta as theta approaches 0 equals 1. We kind of a lot of people don't even bother to prove it, and at a later time they will talk about something called L'Hopital's rule, and then they'll do this, but just for the heck of it. Now, before I proceed any further, let me tell you this: if you don't understand this, that's perfectly all right. I'm not going to ask about it in a test or quiz. However, if you happen to be curious, yeah, this is kind of cool. Okay, all right, and for that we need to consider a circle whose radius is 1 unit, which is what typically people say, unit circle. Okay, and here notice I have a right triangle OAB and another right triangle OCD. Okay, this angle is a right angle, the angle OBA, and similarly ODC is a right angle. Maybe I should have shown that. All right, so we need this particular figure to prove that, and also this is going to be an informal proof. Boy, when it gets to formal proofs, man, people are very strict about how you present it. I don't care about that part. I want you to understand the proof more than be able to write in a paper, in a journal paper or something like that. Cool. Would you agree with me when I say length of the segment AB is actually sine theta? What? Yep, this vertical length AB, I'm claiming that is sine theta. Well, on what grounds can I claim that? I can because look at this triangle OBA or OAB. That's a right triangle, right? And so sine theta, if you remember that SOHCAHTOA, sine is opposite over the hypotenuse. So sine theta should be whatever is the length of this segment AB divided by the length of the hypotenuse OA. But what in the world is the length of OA? That is 1, because that's the radius of the circle, and we already said that the radius of the circle is 1 unit. So we have sine theta to be AB over 1, which is AB. Okay, so that's why I said length of segment AB is sine theta. Next, length of this arc AD, I'm claiming is equal to theta. Where do I get that from? Well, there is a formula, like the arc length of a circular arc is that arc length L is the radius times the angle subtended by that arc. So this arc, the red one, is subtending and is making, the word people use is subtending. What that means is it's making an angle of theta here at the center, right? That arc AD. And so sine the L equals, the length of the arc equals radius 1 times theta. That's what makes it just theta, because r happens to be 1. Cool. Okay, now which one seems to be bigger, AB or this arc length AD? Right? Straight line distance is the shortest distance. So anything, when we are going from point A to this line, any distance, perpendicular distance is the shortest. So if you were to go to AD, that AD has to be bigger. And in fact, this arc length would be even bigger than just straight line distance from A to D. So AD clearly is bigger than AB. That means theta is clearly bigger than sine theta, or if theta happens to be 0, they are both equal. So that's why we say sine theta is less than or equal to theta. I showed you that theta is greater than or equal to sine theta, but then that means automatically sine theta is less than or equal to theta. Okay, good. What else? We can divide both sides by theta, and that would not change the inequality. What do I mean by that? That would not change the inequality. Notice, when you multiply or divide by a positive number, the inequality does not change. However, if you multiply or divide by a negative number, the inequality changes its sign. If theta were to be negative and we are dividing both sides by theta, a negative number, then we have to change this to greater than or equal to. But in our case, we are measuring theta counterclockwise, which is considered to be positive, so we are okay. Next, length of segment CD, I'm claiming, is tangent theta. Which one? That C to D. That is tangent theta, I'm saying. Where did I get that from? Notice, if this is theta, tangent theta is opposite over adjacent. Opposite is CD, adjacent is OD for the triangle ODC. But length of OD is 1 because that's the radius of the circle. So we have tangent theta is equal to the length of segment CD divided by 1, or that's just equal to CD. So length of segment CD is tangent theta. Which one seems to be bigger, the length CD or the arc length AD? That's the comparison I would like you to make. Clearly that CD is bigger than AD, right? In fact, you have to formally prove all of that stuff. You have to draw a tangent at this point and a tangent at this point, and then show that it's a convex hull and blah blah blah. For us, just a visual thing is proof enough. Okay, so CD is equal to tangent theta, but then theta is less than or equal to tangent theta, that is arc length is less than that CD, and so we have we'll convert this into, we'll replace this tangent theta with its identically equal sine theta over cosine theta. Cool so far? Okay. Can I divide both sides by theta and multiply both sides by theta, by cosine theta, in order to get this? Right, I multiplied both sides by cosine theta and also divided both sides by theta. We guaranteed that all these quantities are positive, so that doesn't affect the sign. Okay, so cosine theta is less than or equal to sine theta over theta is what we get from this. Now, we notice that this inequality is cosine theta less than or equal to sine theta over theta, and this inequality is sine theta over theta is less than or equal to 1. Could we combine these two inequalities and make a claim like this? And that would be perfectly fine. Cool. By the way, what are we interested in? We are interested in limit of sine theta over theta as theta approaches 0. Okay. So, in the next step, if we were to proceed with taking the limit as theta approaches 0 of every one of these quantities, what do we get? Limit of cosine theta as theta approaches 0 is just cosine 0. Cosine 0 is 1. Limit of 1 is 1. Please pay attention to this little part. This is the coolest thing next to sliced bread. We notice that limit of cosine theta is 1, limit of 1 is 1, and so automatically by squeeze theorem, limit of sine theta over theta must be 1. So that's where this thing is applied. The squeeze theorem, you apply it in a context like this. Because you know the limits of these two outside quantities, from that you can infer what the limit of the middle quantity ought to be. So thus by squeeze theorem, limit of sine theta over theta is as theta approaches 0 equals 1. Okay, so let me put your minds at ease. If you get it, fine. If you didn't get it, equally fine. Let's move on. Similarly, it turns out limit of cosine theta minus 1 over theta as theta approaches 0 is 0. Otherwise, if you simply plug in 0, you get cosine 0 to be 1. 1 minus 1 is 0 over 0. 0 over 0, it's an indeterminate form. However, if you were to use this proof and do some manipulation and stuff like that, it'll turn out that this is equal to 0. I don't want to go into proof of all of that. Just take it from me. I need these two limits in order to figure out what the derivative of sine x is in a formal fashion. Let's see. We are being asked to find the derivative of a function called sine x. Whenever you are being asked about a derivative of a function for the first time, you know nothing about it. That's when you need to go to the definition of a derivative. Cool? Here, the definition of a derivative we know is f prime of x is limit as h approaches 0 of f of x plus h minus f of x over h. So if we apply that, we notice that since f of x is sine x, f of x plus h would be sine of x plus h minus f of x itself is sine x all over h. Once again, let me reassure you, I will not be asking you for the proof of derivative of sine x. This is just to show you. Okay, so now if we were to simply plug h equal to 0 into this, we end up with sine x minus sine x, which is 0, over 0. So that's an indeterminate form. So how do we evaluate that limit? Now you need to recall a trig identity. The trig identity says sine of a plus b is not just sine a plus sine b. So you cannot say, oh, this is sine x plus sine h, man. No, it's not. In fact, it's a bit more complicated. Sine of a plus b turns out to be sine a cosine b plus cosine a sine b. Okay, so if I apply that, I get sine x cosine h plus cosine x sine h minus this sine x that I have. Okay, all right, what good did this do? Well, if you notice, there is a sine x here in the first term and there's a sine x in the second term. So I can group the first and the third term, factor out a sine x and say sine x times cosine h minus 1. Separate that into one fraction and then have this other one, cosine x sine h over h, limit as h approaches 0. So that's what I wrote here. All right. Now, this is a pretty interesting claim. Can I pull the sine x outside of the limit? Can I pull this sine x, that is multiplying cosine h minus 1 on the top, the sine x just outside? Oh, well, that x is a variable, man. How can you pull it out? Well, the thing is, because we are computing limit as h approaches 0, h is the one that is approaching 0, as h changes by approaching 0, h is changing, that doesn't affect sine x at all. Sine x is independent of h. So sine x, so far as h is concerned, can be treated as a constant. A constant multiple can be pulled outside of a limit. So it allows us to pull the sine x outside and say limit as h approaches 0 of cosine h minus 1 over h. Similarly, from the second limit, we are allowed to pull the cosine x outside of the limit, and that gives us cosine x times limit of sine h over h as h approaches 0. Okay. Obviously, the whole thing is equal to just cosine x, right? Obviously. What'd you say, man? Well, what is limit of cosine h minus 1 over h as h approaches 0? Isn't that just like this? So isn't this limit just equal to 0? So sin x times 0 is 0? Earlier, didn't we prove that limit of sin theta over theta as theta approaches 0 is 1? So this guy is 1. So we have cosine x times 1. So we have 0 plus cosine x, and that's cosine x. That's the ta-da proof. So if f of x is sin x, then f prime of x is cosine x. In other words, the derivative with respect to x of sin x is cosine x. And this you got to memorize. At any time of the day, even if you're fast asleep and I wake you up and I go, what's the derivative of sin x? You got to go cosine x. Well, similarly, derivative of cosine x turns out to be negative sin x. We could go through all this formal proof, but I'm not going to. d dx of cosine x is negative sin x. All right? Now, with that, let's go to d dx of tangent x. Do we have to again do the proof and all that, man? No. Check this out. We can find d dx of tangent x because we already know the derivative of sin x and cosine x. How does that help? You tell me. You already know the derivative of the top is the sin x is cosine x, derivative of cosine x is negative sin x. How will that help us figure out d dx of sin x over cosine x? Give it just a little bit of a thought. Did we learn some rule in the previous section? The quotient rule? Does it look like we have a quotient here? Something over something? Yep. So, by applying the quotient rule, low d high minus high d low over low low, or denominator cosine x times the derivative of the numerator sin x minus the numerator sin x times the derivative of the denominator divided by the square of the denominator, which makes it cosine x, the derivative of sin x is cosine x, minus sin x, the numerator, times the derivative of cosine x is negative sin x, all over the square of the denominator, which is cosine square x. So, on the top, we end up with cosine square x, and minus negative sine square x is plus sine square x. Cool? But wait a minute. What is cosine square x plus sine square x? That's 1. So this is just reduced to 1 over cosine square x. And in turn, what does that reduce to? 1 over cosine square x is nothing but secant square x. Isn't that neat? So derivative of tangent x is secant square x. So I could very well ask you this part. Show that the derivative of tangent x equals secant square x. That means you would have to go through this quotient rule and all of this stuff. Okay? Next. What is the derivative of cosecant x? Derivative of cosecant x. Wait. Isn't cosecant x the same as 1 over sin x? Okay. Now, do we know the derivative of sin x? Yes, we know that is cosine x. Will that help us? Yep, we can apply the quotient rule once again to this. And so the denominator times the derivative of the numerator minus numerator times the derivative of the denominator over the square of the denominator. So sin x times the derivative of the numerator. Derivative of a constant is 0. So we have a times 0. Minus the numerator 1 times the derivative of the denominator is cosine x. All over the square of the denominator. But this just goes to 0. Sine x times 0 is 0. 1 times cosine x is cosine x, but there's a negative. So we end up getting negative cosine x over sine square x. Okay, we get negative cosine x over sine square x. But what I've chosen to do is, I've chosen to write the sine square x as sine x times sine x. And then said, let's look at it as negative 1 over sine x times cosine x over sine x. Of course, this, if you multiply the tops, you get cosine x, then multiply the bottom, you get sine square x, so negative cosine x over sine square x. But on purpose, I split it like this. You will understand why I did that in just a second. Now, what is 1 over sine x? Cosecant x. What is cosine x over sine x? Cotangent x. So that became negative cosecant x cotangent x. So the derivative of cosecant x is negative cosecant x cotangent x. Cool? Now, over here, similarly, the derivative of cotangent x is negative cosecant square x. So look at the kind of symmetry here. Tangent x derivative is secant square x. Cotangent x is negative cosecant square x. Similarly, derivative of cosecant x is negative cosecant x cotangent x, and ddx of secant x turns out to be secant x tangent x. How would you find the derivative of secant x? Well, you write secant x as 1 over cosine x, kind of like how we wrote cosecant x as 1 over sine x. For secant x, we will write that as 1 over cosine x. And how do we find cotangent x, the derivative? Just like for tangent x, we wrote as sine x over cosine x. For cotangent x, we will write cosine x over sine x and then work with it. Okay, you must know how to do all these so-called proofs. Okay, I wouldn't ask you to prove the derivative of sine x or cosine x, but the tangent, cotangent, secant, cosecant, yes. And in addition to doing that, you must memorize these 6. With time, you will have a few more derivatives that you need to memorize. But for now, definitely the derivative of all the trig functions, now we know sine x, cosine x, tangent x, cotangent x, secant x, cosecant x. Cool? There is a sort of symmetry though. Sine x, the derivative is cosine x. The derivative of cosine x is negative sine x. There's something else I want to show you. Cosine x, the derivative is negative sine x. Cotangent x, negative. Cosecant x, negative. So these co-functions, cosine, cotangent, cosecant, they are all negative. Their derivatives are negative. Remember that. And also, the derivative of tangent x is secant square x. So that means cotangent x would be negative cosecant square x. Okay. Usually, the way I operate is, you may not need to. If you ask me what is derivative of cotangent x, I'll say just hang on a second. What's the derivative of tangent x? Oh, that's secant square x. Based on that, I say, cotangent x therefore must be minus, you gotta have a negative, cosecant square x. Just as this is secant square x, that should be cosecant square x. And similarly, I know derivative of secant x. That is secant x tangent x. So if you ask me what is derivative of cosecant x, I don't know. I'll just go to secant x first. Okay, what's the derivative of secant x? That I know to be secant x tangent x. So if you ask me cosecant x, oh, that must be negative secant x tangent x, cosecant x cotangent x. Yeah, that's how I remember these things. But I definitely try to remember them. Okay, next. I'm going to do a few problems. Let's look at this. On purpose, I picked a fairly involved problem. Okay. Do we have the derivative of a product here? First function, and this whole thing under the parenthesis and inside the parenthesis is second function. So first function times the derivative of the second function plus second function times the derivative of the first function. That's what I need to do. And in this step, that's precisely what I did. First function times the derivative of the second function plus second function times the derivative of the first function. So now let's ask, is the derivative of a sum equal to sum of the derivatives? Derivative of a difference equal to difference of the derivatives? It is, right? Okay, what's the derivative of cotangent x? We just learned it. I don't know. I said tangent x is secant square x. So cotangent x must be negative cosecant square x. Yep. So the derivative is negative cosecant square x. But how do we do this guy? Whoa, that's quotient rule. So we'll apply quotient rule to figure the derivative of this. That's what we'll do. And this is just a straightforward function. There's nothing to differentiate here. But then what's the derivative of e to the x? E to the x. So the second term seems to be straightforward. The first one is just a little involved. So let's get busy. So first e to the x, that's what I wrote here. The derivative of cotangent x is negative cosecant square x, like I was talking about. And now for this, I did the low d high minus high d low over low low. Sin x low, d high, the derivative of cube root of x. Cube root of x is x to the 1/3. So the derivative should be 1/3 x to the 1/3. Nx to the n minus 1. I goofed. Samuel. This is the problem when you 1/3 minus 1. I thought it was in the denominator. Negative 2/3. 1/3 minus 1 is negative 2/3. And the cube root of x times the derivative of sin x is cosine x. That looks okay. And this looks okay. Oh, so that's the only change I need to make. Okay, so 1/3, derivative of x to the 1/3 is 1/3 x to the 1/3 minus 1. 1/3 minus 1 is negative 2/3. Okay, sin x times 1/3 times thing minus the numerator times the derivative of the denominator gives me this, and the square of the denominator. And this part I just got d dx of e to the x to be e to the x. Right? You don't need to simplify this. This is perfectly fine if you leave the answer this way. And d dx of cosine x over 1 minus sin x. Let me pause here for a second. All right, I'm back. Let's look at the derivative of cosine x over 1 minus sin x. All right. Simple, straightforward, I think. I think this should be easier than the previous problem. Denominator, we're applying quotient rule. Denominator times the derivative of the numerator minus numerator times the derivative of the denominator over the square of the denominator. Right? Like when I'm saying this stuff, is it going way over your head when I say denominator times the derivative of the numerator and things like that? All I'm doing is that low d high minus high d low over low low. I'm applying it. Instead of saying low, I could maybe, would it help if I simply say low times d high, low being the denominator, d high is the derivative of the numerator? Would that help? D high means d of the high. Let's call this cosine x as high and this as low. Low, 1 minus sine x, times d high, derivative of the high, minus, so what's 1 minus sine x, times the derivative of cosine x is negative sine x, minus high d low, high is cosine x, times d low, the derivative of the low, and that is just nothing but d dx of 1 is 0, and the derivative of sine x is cosine x, so we have a minus, so the minus over the square of the denominator, right? And then that turns out to be what did I say? Minus sine x. Whoa, nearly. Whoa. What I wrote is correct. Huh. Dang. Do you agree that's what this turns out to be? Where did I get that plus 1 from? Okay, check this out. 1 times negative sine x is negative sine x, right? And then minus sine x times negative sine x becomes plus sine square x. And here I have a minus cosine x, minus cosine x times negative cosine x becomes plus cosine square x. So there was a plus sine square x here and a plus cosine square x, which adds up to 1. So that's what I did. And so I wrote a plus 1 here. Okay, but then can we simplify this further? Can I factor out, how should I, yeah, this is, oh, by the way, this is just 1 minus sine x. I can write the top as 1 minus sine x, right? So 1 minus sine x over the square of 1 minus sine x just simply becomes 1 over 1 minus sine x. Cool. So the derivative of cosine x over 1 minus sine x is 1 over 1 minus sine x. So what I feel is, I think I'm done with that section. I didn't solve a whole lot of problems, right? I seem to be solving just 2 problems. That's because I think I have taught everything that I need to. It's you need to practice a lot. Okay. If it is the case that you have questions, then I'll gladly answer them. But please get busy and start solving problems in this section, 3.3. All right.